Hello? Thank you. Oh, thank you.
I now request her to take over the stage.
Thank you. Okay, so I'm going to tell you a little bit about C++. Not so much about individual language features, but something about how I would like to see the language used and what I would like to see it used for and what it has been used for. Because the aim is to get better systems, better code. And, whoops, good. So part of the inspiration is me listening to discussions on the web, in person, at conferences and such. And often I think I'm the only one in the room who doesn't know what C++ is. Everybody else seems to have some really firm idea, and you can see some of them there. And I feel that we have a case of the blind man and the elephant. If you only know one bit of the elephant, you can be really firm in your opinion about what the elephant is. But, well, I know the whole elephant pretty well, its strengths and its weaknesses, and so I'm not quite as certain as most people. So here's my view of what the elephant looks like. It's a language for defining and using lightweight abstractions. That is, you can deal with the hardware and you can build abstractions on top of it, classes, class hierarchies, generic functions, algorithms, stuff like that. That is what it's for. And its key strength is if you are building software infrastructure and if you have resource constraints. Resource constraints can come because you might be writing for a little gadget, a cell phone, embedded systems, or you can build software for a huge server farm. In either case, you're running out of resources if you don't watch out. And there's not one size that fits all. One of the great annoying myths in computer science and programming is that there's one kind of system, and there's one kind of language that's right for everything, and one kind of developer that's equally good for everything. I believe that's absolute rubbish. The different projects have different constraints, different hardware constraints. I mean, there's a Google server farm and there's a wristwatch. It's different in what you're concerned about. Reliability constraints are very different. I mean, if you're building a video game or a website, it's no problem if it goes down once a week. If you're building a life support system, somebody dies if you get an error. These are different systems. They require different attitude, different tools, different ways of writing things. Efficiency constraints differ. How quickly must you do something? How much electricity can you consume doing it? And developer skills differ. Different places, different organizations have different skills. And you have to use the skills people have, and you have to develop those skills in a direction so that you can build better things. And so, and sometimes time to completion comes in. It's, well, right, you can build the perfect airline control system for the United States in 15 years. The problem is that you don't have 15 years to build it in, and so that project got terminated. Fortunately, it wasn't a C++ project. And the extremes then, all that matters is to get it out. Bugs doesn't matter. The other thing is that if you have 50% overhead, you have to buy another server farm. Another server farm costs about 50 to 60 million US dollars. And it takes a lot of energy to keep it running. Really, electricity like a small city. And then there's the light and things. So what we really want is code that are easy to understand for both humans and tools. We want correctness, that is, you read the specification and you hope the specification is precise. And you want maintainability because we spend 80% at least of our time working on systems that are already working. and we want modularity so that we can develop things and change things in isolation from the total system. We want error handling to be systematic, complete, and effective because, well, our systems are large, and even if there wasn't a single bug in your code, which is unlikely, your hardware will break sometimes. I mean, as I said to my students, this is a student exercise. If I kick the power plug out of your system, it's dirty pool. But in the real world, you have to survive if you lose power. So, real world things comes in, you have to handle errors. We have to have effective resource management. A lot of our systems deal with resources. Memory and time are the most obvious ones, but files, sockets, connections to the rest of the world are others. We want efficiency. I'm interested in compact data structures. I want algorithmic structures so that I can understand what I'm doing rather than write on code. And I want things to be portable unless I don't want to. You can't be portable if you have to use a dedicated resource that only exists on one machine. And then today, everything is concurrent. It's global, it's throughout the data center, it's on the web, it's multi-cores, it's clusters and such. So we need to deal with that. Those are the kinds of ideals. They've got nothing particular to do with C++. You should really sort of think of these as universal, but they inform the way I work with C++. And people have been talking about multi-paradigm programming. I've been doing it too. And I usually say, well, this is a phrase we use till we find something better. And a lot of people look at C++ and write it as if it was 1978 in the C style, or in the 80s, see the classes. Then people get the object-oriented bug and wants everything to be a class hierarchy. And people get drunk on templates and want everything to be a template metaprogram. And these days, a lot of people think that everything should be functional. And this is sort of the wrong view. You want a synthesis of things where you can use these techniques where appropriate. And I'll get back to these high-level ideas as I go along. But basically, the idea is that you can use techniques from these fields and get optimal solutions. Whereas if you paint yourself into one of these corners, use only one of these views of C++ or programming in general, you're doing suboptimal. Suboptimal in performance, suboptimal in maintenance, suboptimal in your time writing the code. And so the solution to the problem, whatever it is, doesn't look like that Swiss Army knife. It has to be more elegant, it has to be a better tool. But we need better tools for better craftsmen, for better developers, for better scientists. And what we really want, as I said, is a synthesis. And I'm not going to go into language features or C++ history in any great detail, but C++ 11 is a much better approximation of my ideals. And my ideals have been fairly constant over the years, but it's a better approximation of the ideals than any previous version of the language. We have C++ 11 and C++ 14. Nothing what I'm saying here is science fiction. C++ 14 is shipping. GCC, Clang, Microsoft are very, very close to complete implementation of C++ 14. They sometimes say it's complete, but if you are going to be really serious, you should remember that there has never been a 100% conforming C compiler. It just hasn't happened. It is just that hardly anybody can tell. We are close enough for practical use. C++ 11, C++ 14 are used in systems that you use every day. So this is real. And I'm told to talk about style, by which I mean how do you design things, how to express it. I'm less interested in how you indent your programs and that kind of level of it. It's more how do you deal with errors, how do you deal with data, how do you deal with resources. Okay, so here's the overview of the talk. Anybody can say that they want something grand, wonderful. First, I'm going to say what I don't like, so as to see what the problem is. And then I'm going to go in to show some alternatives. I'm going to emphasize type checking, static type checking in particular. I'm going to talk about resources, data structures, control structures, and then a little bit more. And if you want to get a written version of some of the ideas here, I wrote a paper for IIT Computer a couple of years ago. It's not the same as the talk, but it's driven by the same kind of ideas. So here's something I don't like. There's Qsort, as defined by the standard C and C++ libraries, and it has obvious code like that. You have a void star that shows what memory you want to sort. There's the size of a member, the number of bytes in the memory I want sorted, and then that wonderful pointer function that tells me what is the sorting criteria for the bytes I'm going to sort. I think just about everything is wrong with this example. For starters, I have never in my life wanted to sort bytes. I want to sort objects of a given type, strings, integers, payroll records, not bytes. Something went wrong here. We lowered the level of abstraction to the machine, to the bytes and such. That's wrong. And we use it in this rather peculiar way. We have an example there. I have an array of pointers to characters and an integer m. That's supposedly the number of pointers to characters in that array. And I have a pointer to an array and an integer d, and I can call things that way. I have to have a couple of functions there. One tells me how to compare C-style strings. One tells me how to compare doubles. Okay? But even the hardware knows how to compare doubles. Why do I have to tell it that? Why do I have to tell it the number of elements in the array? I mean, my data structure should know how many elements they've got. Otherwise, I get bugs. And yes, C-style arrays without their size attached is a major source of bugs. So that's something wrong here. And let's look at how we write it. First, we throw away the information of what the type is, so we can pass it to the comparison function. And then we have to hard code and cast back to the original type, or at least to the type we think is the original type. That's ugly and complicated. And look at that compare doubles. There's a single instruction on every machine I've used for the last 20 years for comparing doubles. And then I have to write this piece of code and hope that the compiler will optimize correctly to do a floating point compare. Of course, the compilers these days has magic that you can write there that's not in the language, but these are the kind of problems that you get if you're writing code by yourself for this level of abstraction. You're throwing away information and you're trying to regain it. And look at the code here. This is inside the Qsort. I looked up for this talk some implementations of Qsort. I found about 20 on the web easily, out of which 3 were real. They haven't been faked by saying, for instance, we're only sorting integers, which is what we do in education for simplicity, so that you lose the whole point. And you find code like this. This is how you swap bytes. This is the kind of manipulation we do with pointers to find things. And then there's a lot of indirect function calls there. Swap is the macro up there, and then there's some go-to sprinkled in. This is the GCC implementation of Qsort. It's one of the best ones around. But boy, it's ugly. And writing that kind of code is error-prone. It's that kind of messy code that makes it easy to make errors, and it makes it easy for the errors to hide when you want to find them. I mean, if you have made a mistake in this kind of code, the code review is unlikely to find it because it's so messy. So, am I being unfair? I don't think so. I picked on Qsort because it's very well known, It's been used for about 30 years, and it's all over the educational world. Even though they cheat and have simplified versions of it, it's simply a Qsort with a few twists to it, but it's real code. And it's comparable to lots of other really low-level C code. And I really don't like the look of it. I really don't like to maintain code written in this style. So I really would like to get rid of it. I think these days there should be hardly any code like that. It's not uncommon though. And if you think this is bad, go and look at some bulletin boards, see the questions people ask, and see the horrible answers they get suggesting you should write this. And a lot of students like to write this code, they want to write this code, because if it's that ugly, it must be efficient. At least that's what some people think. No, it's really, really slow. I mean, look at those indirect function calls there. That's slow. There's few things that modern processors dislike more than indirections, especially when they're for function calls. And that swap there swaps bytes one at a time, and you hope the compiler will swap words instead where it can. But you're only hoping, not all optimizers will do it right, so it's not efficient. So why else would people do it? I mean, it's cool. If you can understand this, you must be smart, right? So you can show off to your friends who can't understand this gibberish. That makes you smart. But for some definition of smart, not the ones that generate quality code in large amounts. And so the idols did it, or does it. You look at sort of code written by superb programmers like Ken Thompson, and people forget that was what was done 40 years ago. And anyway, they're not Ken Thompson. So that's not good. And it's not just a C problem, but it's very prevalent in people who has a C view of C++. And it matters. I think that style, or lack of style, is one of the major problems with modern C++, because it's not modern, and poor teaching does massive harm. It actually destroys a lot of code before it's even written by getting students to write in styles that are hard to maintain, hard to understand, and inefficient. The C first approach, where everything should be C until you get the advanced C++ features, put off lots and lots of students who never learn the elegance of writing higher level stuff and doesn't believe it works. And it does. And then there's the people who writes everything as class hierarchies, which is fine for some applications, but not all. And this talk is about how we can and should do better than this. So what do I want? I want, first of all, I want some nice, simple interfaces. So if I want to sort a container of elements, I don't want to sort memory with sizes and number of elements, explicit and comparison functions, explicit, all this. I think we want to say sort the container. You can do that in C++ 14 plus concepts. That's the only way you can do this just now, elegantly and simply and generally. You can fake it pretty well, but this is what I want. And this is what I'm going to get very soon. That code up there, sort of container reference, will be a C++ ISO standard technical specification in a couple of months. Simpler calls, I can do that already. If I want to sort a vector of strings, I should just say sort it, and it'll use the usual sorting rules for vectors of strings. And if you want to sort the different rules for strings, you can supply the function. But by default, you don't have to part it. And I don't want to compromise performance. C++ is a language for resource-constrained systems, for high-performance code, among other things. So it should run faster. And yes, I can make that stuff run significantly faster than the Qsort we saw before. So high-level code can actually outperform low-level code if you're very, very careful about how you define the things. And I don't want any static type violations. I basically don't write them anymore. The language is rich enough that I can write my code without static type violations. And I don't want to leak anything, file handlers, thread handlers, memory. That's always already done. There are styles of C++ usage that makes that very easy to achieve. So we want to write a more type-rich program. We want to express more directly what we want. And I'm going to show a bit about that. So if we look at interfaces, there's some common ones up there. Increase the speed by a double, draw an object, draw a rectangle described by 4 integers. These are very common interfaces, and they're very uninformative. What does that double mean for increasing the speed? Is it the speed that you want after the increase to that speed? Or is it a delta? That amount? It doesn't say so. Similarly, what does it mean to draw an object? Yes, you can guess, because I used a very, very common operation, but maybe you guess wrong. There's nothing there to guide us. And what does those 4 integers mean? Probably the first 2 is x and y coordinates of a point, but what are the second 2? And better interfaces are more precise. Increase the speed to a speed, draw something for a shape. Now we know what draw means for a shape. That object up there may not have had a draw function, in which case we would have a runtime error where we could have a compile time one, or it could be a part of a game simulation where draw meant put a run. In other words, you want to be more precise about it. And the rectangle here, if we are more precise about whether we have another point, whether we have 2 points or a point or a box shape, we can be precise that we can catch a lot of errors. And this is important. That picture there is a Mars climate orbiter. About 10 years ago, it came up to Mars, and it started the maneuvers to get into orbit around Mars, and it disappears. There are certain theories that the Martians had kidnapped it for ransom money, but the real explanation is more sort of mundane. There was one group of engineers that had used the MKS system, the SI system, which all scientists in most of the world uses, and another group of engineers had used the imperial system, gallons, miles, and such stuff, and a double moved through one of those interfaces, changing its meaning by 4.65, it's the exact conversion factor for some pressure issue. And that satellite disappeared, and was never seen again. I checked the cost. It was about $650 million US, and that's to compare is about the lifetime's earnings in the US of about that third of the room. I mean, that many engineers, their whole life work went down the drain, right there, just because of a mismatch of units. I mean, we all know how to avoid this. Those of us who had physics in school was taught never to do a calculation so you make sure that the unit made sense. And people don't do that. So let's see what we could do. Here's what we should have done. Units we could have used. Here we have speed as meters per second. A speed is not meters by second squared. That's an obvious error. Speed is not something without a unit divided by seconds. It doesn't make sense. It doesn't exist in physics. And acceleration, yeah, it's a speed divided by seconds. This is what we learned in high school. So why are the engineers doing this? Why did we lose that space probe? It's because no general purpose programming language supports units directly. And special purpose languages have been defined again and again and again, but they aren't used because they don't fit into the tool chains, and they have too few users. Then every language can do this at runtime by building little conversion functions to check before you do the computation, but they cost things. In particular, they cost memory, and there's very little memory to spare on these space probes, and it costs time, and they have poor little processors, so time they don't have either. So people don't do it. And quite often people decide, we'll just keep track of it, we won't make unit mistakes. And most of the time, people are right. So instead of taking double the memory, double the time, they just do the calculation on their little notepad, and they get it right almost all of the time. Except for the Mars Climate Orbiter, and that was 200 lifetimes worth of really good engineers down the drain. So we can do that. So let's see, what can we do? We can't change the general purpose languages to have the MKS system in, because then everybody else wants something either. I know the people who are doing currency trade would like to have conversions also. It's a totally different kind of conversions. And building all of these kind of unit systems into a kind of language is not a good idea. We don't want a multitude of special purpose languages either, because that doesn't seem to work either. So we'll try and build it as a library. And we've been able to do this in C++ for about 15 years. So here's how to do it. We define a unit. A unit is either M for meters, K for kilograms, and for S for seconds. And we make a value of something that has a unit and a double, which says the magnitude of what we're talking about. And so I can define speed as a value which units are 1 meter, no kilograms, and divided by a second unit. Fine, that's expressed. I can take the acceleration too. This is fine. So we can do it. And we can then write our problem like that. Speed is that kind of value divided by that kind of value. And of course, the engineers scratch their head and say, you want me to write that nonsense? They don't want to do it. So we define something like M that represents the unit of meters, and S that has the unit of seconds, and that works, but they still say it's too complicated, and what are those brackets doing? Especially the physicists are very rude about this. This was tried at the Fermi labs. We can try meters per second, and now we have to have a lot of names, and anyway, people don't really believe that we're typing that much. Remember, doing it the bad old way that gives a bug every decade, you would simply write 100 divided by 9.8. You would also, in the low-level system, if you say 100 divided by 9, you get the wrong result. But this is not fine. So we went down to M of 100, S of 9.8, because everybody knows that M stands for meters and S stands for seconds. But no. The engineers said this was too cryptic, and the physicists said that it was too expensive because obviously there was 2 function calls there. And nothing we were able to say convinced them otherwise. The fact that they were wrong didn't make a difference. People are very attached to notation, and they are very attached to their sort of mental model of the universe. And the mental model of the universe for the physicist was that parentheses are function calls and they are slow. The fact that C++ eliminate all of that didn't get through to them. So we have to get the syntax right. And so in C++ 11, we can actually do this. We can define seconds and units as names for those units. And I can define what it means if a literal followed by an S is seen in the code. Those operator literals, where the double quote means literal, says what the meaning of a long double followed by an S is. It's the double in seconds. And if you have the literal followed by S2, it's that number in second squares. And now, whoops, this code is now running C++ 11 code. And it executes at exactly the same speed as the code you would write without units, and we can now express unit systems directly in the language. So by doing this, we can get a type system that is far, far more fine-grained than just integers or doubles. We can actually get seconds and meters and miles per hour or whatever you like at no cost at runtime and immeasurable time at compile time. So the style lesson here, I think, is that we want to have very fine-grained types. We want strong typing, but we want stronger typing than just integers and doubles. The thing that's wrong with integer, double, and string is they can represent just about anything. And we don't want our interfaces to accept anything. We want our interfaces to accept the things that we want them to accept. So if I want to increase the speed with a delta, I should take an integer or a delta if you define that. But certainly if you wanted to increase it to a speed, we want to take a speed, not a double. And so double object and interfaces are a way of getting bugs. And so we want to get rid of that if we can. Changing the gears a little bit, one of the problems I deal with a fair bit when I think about systems programming is resources. And a resource is anything that you have to acquire and then give back. Memory is the obvious example. Sockets, thread handles, file handles, things like that. And we have to give them back because they're usually a limited resource and the system wants it back so it can recycle them. Ideally, we are not doing this explicitly. Explicitly, resource handling is error-prone in any language, so we want to avoid it. And so I'm going to show you how to do that. There's some pictures on my slide that are mostly something to do with the C++. That happens to be the world's largest ship in the harbor of my hometown of Aarhus. I trained some of the people that programmed the design software for that. There is some connection somewhere for these pictures. Okay, so here is a very classic, simple and wrong program. I open a file, I use the file, and I close it again. And this is fine if it looks just like that, but if we if I in there put a return statement or throw an exception, I would never come to the if close, and we would have leaked the file handle. And it actually used to be one of the more popular bugs in browsers, which meant that if you looked at enough pictures, which are files, you would eventually run out of memory because file handles, because they leaked. And so the problem here is that it's obvious to us that the pointer coming out of fopen is one that has to be given back to fclose. But it's not obvious to the compiler, and it's not obvious to somebody who doesn't know about fopen and fclose. The problem is that we have one of these very general things. We have some pointers to files, but it doesn't say that the pointer coming out of fopen has to be given to fclose later. The notion of a resource that is in our mind is not there. So a lot of people then develop the equivalent of this program to solve that problem. That is, we fopen something and we catch exceptions. Unfortunately, this does not take care of returns. We catch the exception and then close on the way out. Everything is handled right. But just look at it. That's pretty nice code. I can understand this, I can maintain it. This is a mess. We've tried to solve a simple problem by making the code more complicated. And there's two things that correlates really strongly with bugs. It's lots of code, more bugs, and more complicated code, more chance of bugs. So this is the wrong way of doing it. And so I went back and looked at it, and the fundamental thing that's wrong with this example is that there are no resources there explicitly. So let's make the resource we're talking about here explicit. We have a file handler, as a file handler class, and you can open it, and when the file handler object is deleted, goes away, we close the file that's associated with it, and that means that that piece of code down here now is shrunk to even less than the original. It says, give me a file handler for file name S open for read. So we have this model, there's a handle that controls things, and it controls the thing it controls. And we can have a scope like it. Fine, problem solved. And this was known as the horrible term resource acquisition with initialization. And I had a bad day when I was naming that one. But anyway, it's a very powerful technique. It's used in the standard library for memory, for logs, for files, and threads and all that stuff. It's pervasive. And basically, so we can do things like grab a mutex. A mutex is a system resource, so it has to give it back. So what we do is we have here a mutex and some data it protects. And down there, we can take a unique log to the mutex, manipulate the data in the shared resource, and when we go out of scope, the mutex is unlocked, it's released. And this kind of style is very powerful. I use this example to show that when I'm talking about resources, I don't just mean memory. So let's generalize this a little bit. Here we've got a function. I want a new gadget, and so in the best object-oriented style, I make myself a new gadget. I'm not going to tell you what a gadget is. It's something that does things. It may have resources in it, sockets, strings, memory, I don't know. But anyway, look at that code. Sometimes it throws, sometimes it returns, and in the sort of the very old, almost C style of code, we have to have a delete in the end. And so people used to Java, C# and says, well, I want my garbage collector. But the garbage collector will not help you there because the gadgets may very well have resources that are not just memory. We have to handle non-memory resources. You could say use the dispose idiom, but that is still explicit and anyway came into those languages a bit later. What can we do here? The obvious thing to do in some sense is say I want a shared pointer. A shared pointer is one that owns the object, and so if we get out of that function by falling through the end of the function, by returning, by throwing an exception, any of those cases, the shared pointer takes care of deleting the thing if it's ready to be deleted. But why a shared pointer? Well, it's traditional. People have been using it for years. It's a safe form of garbage collection, so people do it. But you know, I'm not sharing this object with anything. So it's mine or mine. So I shouldn't have a use count going up and down. I can solve that by using a unique pointer, which is a facility in C++ 11 that represents unique ownership, and is very useful for speeding up old programs and the shared pointers in it. But you know, why am I using a pointer here at all? I should have used just a local variable of the gadget and gotten over with it. The reason I use this example is I am actually seeing more and more code that looks like that, because people have gone to a Java class, learned to put new in front of everything, and now they have to write deletes and now they can quite rightfully complain that deletes you can forget them and they're no good. Anyway, so I have one more problem to solve before I give the style lesson for this, and that is one of the reasons there's a lot of pointers in old code is the problem of how do we get a lot of data out of a function. I mean, think of factor function, think of things that builds up a container, and quite often you then have a large object and you pass a pointer out. And that unfortunately implies explicit memory management. You can use a garbage collector, you can use counted pointers, or you can do it by hand. The first two implies unpredictable delays and overhead. The second doesn't work on a large scale because you leak things. And so this is a noticeable source of both complexity and errors. So we have to do better. So let's think about this problem, how to get things out of a function. And my favorite example is I want to do matrix operations. I want to do a matrix add. An add of two matrices yields a new matrix. So it's a one-off way of creating an object, and it has to get out of there somehow. And we can use a pointer, but that spoils the notation. We've just lost about 300, 400 years worth of experience of how to write mathematical code there. We can return a reference. Now the notation looks right, but you still have to go around and deleting the object that was created. You pass the point on the free store, you pass the pointer out. You have now obscured the problem. It is not a good idea just to obscure a problem so that you can't see it. The code gets prettier, but the error is coming. There's a lot of cases in code, new and old, where people are proud of disguising a problem and then hoping it doesn't happen. This is not the way of writing quality code. We can return a smart pointer, but then we're back to notation, and we're still doing pointers. And the obvious right solution is that if you have a function that creates a new object, let it return the new object. The problem with that is that copies are expensive. And so for a long time, people have sort of returned an object. And in the standard computer science way, you return object by copying. But only computer scientists would do this. You knew better when you were about 6 months old. Look, here's an object. Now it's over there, there's nothing there. I didn't do any copies. Only a computer scientist would make a copy, put it over there, and then destroy the original. That's where the inefficiency comes in. So if we instead return a handle, which are really easy to copy, of course, then the problem goes away. And this is what we can do now. We can write the operator plus. We make the new matrix, fill it up with data, return it, and then we can get the code we wanted. And the way that's done is actually we simply make R, fill it up with data, and then we take the pointer, move it up there, and zero up the first pointer. It's a general way of getting a lot of stuff out of a function. Now, the code for writing that in C++11 simply use this ref thing to say that you're dealing with a loop constructor. You always copy the representation as a handle, and then you zero out the handle, and that is done. This is the way you can get 10 million doubles out of a function at the cost of maximum 6 assignment operations of words. And that move semantics is pervasive in the standard library, and it works not just for initialization but also for assignment, where it's very hard to get the optimization done without language features. So basically I recommend no naked pointers in the code. if you have to have pointers, you will use unique pointer or shared pointer. Don't have new and delete in your code. They belong in the implementation inside constructors, destructors, operations like that. Return objects by value. And so I'm going to point out that garbage collection is not an ideal solution, and it's an incomplete solution. It does not deal with non-memory resources. And if you think about finalizers, you should read up on the horrors of those. Even the best Java programmer says never use a finalizer. So here it's incomplete, and it's also flawed. In modern systems, if you're interested in performance, if you're interested in reliability, you try not to have shared resources across the whole system. So if you've got, say, 20 processors, you don't really want them to share anything. The best performance, the most reliable code doesn't share between the different cores. Shared memory is dodgy from all perspectives. And saying that there's a garbage collector that owns all memory means that you have to solve the problem that you just made memory a shared resource among all the cores. So it's not ideal. And I said we needed pointers sometimes, like a shared pointer and unique pointer, and the place where we do this tends to be when we do object-oriented programming, but we can actually use things like make unique, which says make a circle there, make unique a circle, and give me back a unique pointer to it, and that means that the new has been hidden inside the make unique function, and you don't have to worry about it anymore. So when I look at code, I look for deletes, because I know if there's a delete somewhere, there's probably a leak, there's probably a bug somewhere. And next, I look at news, because when there's a new, there has to be a delete somewhere, and if I can see the new and not the delete, there's a good chance there's a bug somewhere. And so I would much rather write in terms of make unique and make shared. Unique if you really own this object, shared if you might want to share it with somebody else. And prefer make unique and make shared to direct use of unique and pointer and shared pointer. It's simpler and usually more efficient. They can do some packaging of objects. And I'll point out auto there. Auto is the facility in C++11 that says give me an object of the type of its initializer. This was a feature I first built in 83, 84, but it got kicked out for C incompatibility problems, and I had to wait 20 years to get it back again. But it's now very popular in modern C++. Inheritance, which is a key part of traditional object-oriented programming. Use it when you have something in your domain that requires inheritance. Do not use it just to be cool or just because you think member functions are nicer than freestanding functions. You use inheritance when you have to, you use encapsulation when you have to. It's one of the techniques. And one of the effects of using inheritance is now you have to manipulate everything through pointers and references, so you tend to get greater overhead. So anyway, limited. Use language features in general to the areas where they're needed. So I'm going to look at data after looking at code structure. And here's an example that I was presented to by John Bentley many years ago. He came into my office at Bell Lab with a big smirky grin on his face. And says, I've got a problem for you here. Look at this. I'll give you a sequence of random integers, like 5, 1, 4, 2, and you insert them in a sequence, keeping the sequence ordered. And then when you've done that, in other words, 5, 1, 5, the 1 comes in before the 5, 1, 4, 5, 4 goes to 3. That's easy enough. And once I'm finished, I'll give you a set of positions, and you yank things out in the order for each position as you go along. So the first position is 1, so I take 2 away, the next one is 2, I take the 5 away, and so on. And so it says, I can represent the sequence as either a vector or a linked list. For which n is better to use linked list rather than vector? And I knew, like everybody else, that lists are really what you need when you want to do a lot of insertions and deletions, and I'm doing insertion and deletions all the time here. So obviously the answer has to be a linked list. But Bentley had a big grin on his face. This has to be a trick question. So I thought about it a bit and said, 1,000? And he laughed and showed that vectors beat lists up to about 10,000. This is a long time ago. So I had to figure out why. Why? So I looked at this again. I've been running it over the years. And there's an example from a couple of years ago. This is the time needed to insert and delete the lists. This is the vectors. The vector is always better than list for this exercise. Don't confuse the exercise with the problem I'm trying to solve, but let's just look at it. I looked at this and I thought, well, I know why this is. Linked lists require a lot of allocations and deallocations. It must be the allocator. So I built a version that pre-allocated everything in the list. Yeah, it's much better than the plain old standard list, but it's nowhere near like the vector. Look here, this is, the x-axis is in 100,000 elements, that's second. So this is bad, this is very bad. If you run this example again for yourself, I suggest you do, it's a good example. Remember, your mileage will vary. Depends actually critically on your machine. But let's look at the the ideas. The next idea was that a linked list takes up more space than a vector. If you have a vector of n elements, it's n integers plus 2 or 3 words to control the vector. If it's a linked list, it's n times the pre and post pointers and the data and the free store information. That's usually 2 words. So here we have 5 times as much memory used as the as you did for vector. So I thought, okay, it's all that memory. But that's not true either. Look, I'm only taking 100,000 elements, and I've got 8 gig on my laptop. That's not it. So finally, I did what you should have done in the first place, which is meshing. And everything goes on in the linear search. To insert something, you search till you find the insertion point, and then you insert, moving things at the end if you're a vector. But you know, linked lists are really bad for linear searches. You do this sort of all over your memory. So you have the pointers, you're scrambling all your cache lines, and the thing slows down. And it doesn't slow down a little bit. Show that graph, it's a factor of 25 or thereabouts. Even though in the vector case, if I insert something in the middle towards the end of my experience, there will be on average 250,000 integers that has to move 1 over. It takes hardly any time on a modern computer. They are really, really good at doing things that systematically shoves you through memory. And people say, well, you didn't know your data structure is right. You should just have used the map. No. 1, I know my data structures, and 2, Bentley is an expert in data structures. He knew exactly what he was doing. He was getting an exercise to try and see what happens when you manipulate data in memory. You should learn from the exercise rather than optimize it. Anyway, I tried again to see what lessons I can get out of it. First of all, don't store data unnecessarily. If I could have made something into a constant thing done at compile time, I wouldn't have any of these problems. In a lot of modern C++, you you just compile things in. You can express things to be computed at compile time. Secondly, keep the data compact. In this case, it didn't matter too much because there wasn't too much memory, but for a lot of real problems, small computers and server farms, the amount of data matters, and access memory in a predictable manner. That's a really key lesson from this thing. And by the way, the data structure I tried with a standard map, which is a red black tree, and it's almost, but only almost as good as the vector. And remember that the vector here is running log n algorithm, is running O n algorithms, and the map is running O log n algorithms. So complexity theory is a very rough guide to what you're doing. If you look at this, I'm not violating any laws of theory. As a matter of fact, I'm using the same generic code to do it with lists and vector. So obviously the complexity is the same. However, the effect on your machine architecture, your cache architecture, is really important. So I'm actually trying to tell you something about real computer science. You have to know your algorithms, you have to know the data structures, but you also have to know your machine architecture. Just abstracting away the machine means that you can end up paying a factor of 25 quite easily. Now, some people say, but I don't use lists of 500,000 elements. Actually, neither do I, but I use a lot of smaller lists, and then the sum is up there. Furthermore, some of the Google guys, the financial guys, don't use lists that are that small. But then you can use segmented data structures and all other things. So this is an interesting example. And you can do it to yourself very simply. Here is a little data structure that's similar to a lot of things we do. It happens to be a vector of points. There's 4 points there. And the standard C++ layout is like that. You just lay down the elements in memory and you keep track of where they are and how many of them there are. And if you want to access them, there's one indirection. If you loop through them, there's no indirection because you just go to the next one. If you are going to a truly object-oriented architecture, think Singular, Java, Python, etc. If you're actually using data structures, you get this. The abstraction is an indirection to an object, and this goes on recursively. That means that to get to anything, you have to have about 3 indirections. If you optimize, if you run through it, you get 2 as opposed to 0 here. And the amount of memory used for this is about twice as much. So if you don't watch out, you can actually do things like this to yourself without even seeing it in the source code. You have to understand what your compiler does to you, what your data structure does to you. So use simple and predictable data structures. Don't store more data than you can. Access to memory is a dominant cost in modern computers. But we also have to look at the control structures. And there's a lot of stuff in C++ that tries to make standard the most common algorithms. The simplest one here is find in this sequence from the beginning to the end Grail, and compact comes a pointer to it, and we can see if we found it. We can find something based on a predicate. This predicate is a lambda, which is a function you define in line and use it, and again you can find it. This is the style of the STL, which has been part of C++ for the last 20 years. But basically the interesting thing is your generic in the container type. This can be word for vector and list, element type, string and integer, and on the operation. So it's all generic, very general, very useful. And we want to use that kind of stuff if we can, instead of writing general code. So here is an example that was presented to me over lunch one day by somebody. They had the problem of having a thing in a GUI where you had to pick up something and move it somewhere else in the list. It was in a menu, but to do that. And the guy who wrote it had the code written, 25 lines of code, 1 loop, 3 tests, 4 machine function calls, standard code like we were all write when we start out, and don't think too hard about it. Then it was messy code. That's a pile of spaghetti. That's the way code often looks when you're not thinking about the algorithms. And is it correct? He tested it, so he was pretty sure it was correct. Pretty sure is not a very strong statement. Is it maintainable? No, because the guy who wrote it wasn't sure and had to look at it several times to convince himself. Is it usable elsewhere? No. This was very special purpose code for a particular GUI, for a particular operation, and that GUI is not portable. And now, this is where the professionalism showed up. The guy who was quite a senior programmer looked at this and thought, this isn't good enough. He asked for a review. And after looking at this for a while, they found that actually, what are we doing? It's a find if. You find the place that you're going to put it, and then you put it there. So basically, find the thing that contains the coordinate where you're putting it, then rotate, put a thing over, it either goes to the left or to the right. So the code became this. It's comprehensible, it's maintainable, and it's special purpose. The reason it's special purpose is that was a vector used in that particular GUI, not a standard vector. And coordinate, obviously, is the string coordinate in that particular GUI. They worked a bit harder at it and came up with this algorithm, which I'm not going to explain in any detail. We do a stable partition that takes things that are before a predicate is met, and the stable position after a predicate is met. Okay, this is standard code. You have to look it up in the manual to figure out what it is, but it's very well defined, and it's general. We're using a predicate, so we can now take anything that meets the predicate. One of the things you could do was to move a collection of elements into a position. For instance, shift, click, 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 choosing 3 elements and moving it over. And this stuff has been implemented and been used in open source software for about 10 years. It works very widely. The thing that's difficult about this is that this code is only obvious to somebody who is reasonably expert in the standard libraries. I mean, even I had to look it up. And one of the things that made some of us programmers is we like to write programs. We don't actually like to read manuals very much. And we have to get to the level where our code is not this spaghetti stuff that can't be maintained and can't be optimized easily. We have to get to a point where we express things in terms of algorithms that can be understood, documented, precisely specified, precisely tested in isolation, and all of these good things, and optimized. So we have to go there. I think this is really, really important and probably the hardest thing to do, to get programmers to write less programs and read more manuals. We have support for generic programming now in C++ and a version of it. That's important because you can't go to algorithms without making them generic so that they can be worked in different areas. So here is what we can do in C and C++ from day 1. We have a double, and we can have a square root, and we can catch errors. In C++ 98, we could have a sort, and we could sort something in a range, and we would get a horrible error out of a mistake. The type system couldn't really express this well. In C++ 14 with concepts, we are getting to the point where we are actually equivalent to the simple code that we've been writing forever. We can say, I want to sort a container and give it a container. Or we can have a sort of a container with a predicate and then give it the predicate. So instead of using the default sort, which is less than, we could use greater than. So we can express algorithms very effectively. And so basically focus on algorithms, consider large functions suspect. A large function, we can argue what that is. I think more than about 10 lines is large. Certainly most people will agree that a function that doesn't fit on a small screen is large. If it doesn't fit on the screen, you know where the bug is? Probably on the part that you can't see because it's above or below the screen. Okay, stay high level. I did some experiments with style. You have a free choice. You can write old loops, or you can write things with algorithms and lambdas. There are no difference in speed. So if you like the first one, fine. If you like the second one, fine. But don't use performance as an argument for it. The performance is identical. I checked 20 ways of writing such a loop, and I couldn't find a difference. And you have to measure. It's not good enough to look at the code and say, well, this looks smaller and simpler, it must be faster. No, have to measure. Your intuition is not good. And also, low level doesn't mean efficient. Qsort is ugly, but it's also slow. Those indirect function calls cost a lot. Those swaps with bytes are not always optimized very well. So your mileage will vary. Last time I did it, the C was 2.5 times slower than the C++. In other words, the low-level C was slow, the high-level C++, which is type-safe, generic, general, and such, was faster. And the reason type safety gives more information to the optimizer, and in particular, you have inlining that works. So if you write traditional C style, you get traditional C style performance, and no more than that with traditional C style bugs. If you do object-oriented code, traditional, you get traditional performance for object-oriented code, and no more, no less than that. So if you want to do better than what we could do 30 years ago and 20 years ago, you have to do something different. You can't just do the old stuff and expect magic to take care of it for you. Furthermore, remember, processors are not getting faster anymore. You cannot rely on Intel to speed up your code for you. At least you have to go to concurrency, and that's hard. So don't lower the abstract level without reason. You get more code, more bugs, more maintenance cost. And here's a little rant of mine. I don't actually believe in paradigms. They have this implication that there are good paradigms and bad paradigms, and good paradigms, which are always the new ones, will take over from the old paradigms. The guy that invented object-oriented programming, Chris Newgall, used to say to people, you know, in the old days we were using plus and minus, but we have this new paradigm, multiply and divide, and we should do multiply and divide because it's new and it's modern, it's fancy. And obviously the story is absurd. There are things for which you need multiply, but there are things that are really, really good when you're doing simple addition. And by the way, subtraction doesn't fit very well with multiply and divide. The point is that you don't have the paradigm replacing the old one, you complement it. And that's what I'm after. So here's an example, which is a classical example from actually Chris Newgall's work of drawing a container of shapes. And you look here, draw all as a container of C. Then I check that the type is what I expected, shape with pointers, and then use the algorithm for each in C to draw. Now, is this object-oriented? Obviously it is. It's a classical example of object-oriented programming. It has runtime resolution of type. It's polymorphic. It uses a base class with virtual functions. It's as object-oriented as it gets. Is it generic? Obviously it's generic. I didn't say what the container was, whether it was a vector or a list. and I used a generic algorithm for each, which is designed for all kinds of things. Is it functional? Well, we can argue that, but it certainly has functional looking things like for each and lambdas, and it's traditional programming, very traditional. So it's all of the above. I'm running out of time, probably did run out of time, so I'm just going to go very briefly with concurrency. Everything we're doing has to deal with concurrency eventually, so the rules I've laid out here, stay high level, stay type safe, is even more important. In C++ 11 gives you the old threads and locks mechanism type safe. No more macros, no more void stars to do threading. It's much easier to write code. Threads and locks are the worst possible way of writing concurrent code, but it's what 99% of what we're doing are, so we have to deal with this first. This is what your system is doing. So we need to do more. Here's a simple threading example. I have a function f, I have a function object capital F, and then I can start f giving it a vector argument. I can start the other f capital F with a vector argument. The threads run, they get joined, we're finished. This is the way we've been writing code since the Stone Age. We can do a little bit better. We have to do a little bit better. And there's a lot of work going on. For C++ 17, it's one of the major directions of new work is to get higher level concurrency models that are easier to use and run faster. We are going to get both. And I'm pretty sure we're going to get it for the simple reason I've seen the proposals and I'm likely to be accepted. And so here's the simplest new thing we can get, this async. It says launch f with a reference to some vector, launch g with a reference to some vector, and get the results back. Async gives a handle back for the future that you can get values from later. If you try and get before the answer has arrived, then you delay. If the answer gets there first, you will just carry on simply. So simplifications like that are possible today. This is standard C++. And it is going to run faster with some probability because you don't need more than one extra thread to run this. You can run the other one on the main thread. So basically, practice time-rich programming, have an integrated resource mechanism management, general resource management and error handling, use compact data structures, try and move towards a more algorithmic style of code, and build and use libraries because writing anything in the bare language is somewhat painful. This is true in any language you can think of. But given sufficient good libraries, just about anything is elegant and easy. And one of the things we work on a lot with C++ is to make sure that those libraries are efficient also. So the modern thread libraries are more efficient than the old style. The standard algorithm by Qsort is more efficient than what you can handwrite yourself with any library. That's good. Of course, nothing is perfect. I'm not going to tell you that we have a perfect programming language. So there's a whole list of things we have to work on. And this is very similar to the list of things that I said I wanted. In other words, I'm not happy yet. There are a lot of stuff that can be done better, and we should. The people who tell you that everything has been done are wrong. There's more information, and then questions. Yes? Is there any microphones we can give to people who ask questions? Because in a room this size, I'm going to have trouble hearing them. Yes. Yeah. Try the phone. It's and maybe it would be a good idea if you came down to the phone, to the microphone, rather than trying to...
The viewers are requested to remain seated. We now proceed for an interactive session with Sir. Note that the doors will remain closed until the end of the session, and now all of you are invited to ask him questions.
Rahul sir, firstly welcome to India. It's really great to see you in person. I have two basic questions. As you were discussing about designs, and I'm basically a Java developer. I've worked in the industry as a Java developer. So my way of solving problems is creating lots and lots of classes. If I have to create one class, I would think twice and thrice of creating super classes so that it is more abstracted. I will create more objects. Now since I'm into research, I'm again following C++ and I want to develop my projects in C++. So means can I borrow the design patterns and the way of modeling an application from Java into C++?
You can take what you have in Java and ignoring libraries for a moment, you can transfer the design directly into C++, and I don't recommend you do it. The thing you should do is through an interface, or can it be done at compile time? If it can be done at compile time, maybe make the interface a function that's a generic function and let that pick the right thing. Furthermore, you get a lot of hierarchy variations in Java where in C++ you take an argument like a comparison object in the sort function. So if you are starting from scratch, you start thinking about can you do it in terms of generic code and have basically static polymorphism. And if you are converting existing designs, first use the smart pointers and then again try and see if you can eliminate some of those class hierarchies. Because if you do, your code gets shorter and it also runs faster because you have more objects. But it's always hard to move from one language to another.
Thank you so much. I have one more question. Like, there's also one kind of design that's trending, like people want to develop very quick prototype codes, like especially in research, you develop quick prototype codes and then you implement it finally. So would it be nice to use Python with C++, initially develop a quick prototype in Python and then slowly convert the modules of it in C++?
There's a lot of people use the prototype approach, and it's always good to get a system running so that you can see where you design is weak and to test it. On the other hand, it's often hard to transfer design from one language to another. And so sometimes people get stuck in a prototype language. And one of the things you get with any dynamically type language, Python, JavaScript, etc., is that you need a lot of testing because you don't have the type system to help you. And one problem with that approach is it's easy to fall into some unprincipled programming using uptime. That is, I really do like interfaces, and I do like them strongly typed. I just want emphasized everything. That's really hard to do in a prototype language. And so when you prototype like that, you have to sort of look ahead and think about what you might like to do in the future, and not just have as fast as you can, but try to ensure that you're doing a prototype of something that can become a production system.
Thanks. So just one request, can you share this
Somebody
slide
else
on your website? Can you share this slide on your website?
What slide?
This slides.
Oh, can I share the slides from this? Yes, I will give it to somebody associated with the Techfest.
Thanks.
Sir, what do you think is a better invention, either Windows or Apple?
Sorry, again?
What do you think is a better invention, either creating the Windows or the Apple?
not going to explain, I'm not getting the question. What? Windows or what?
Apple.
Or iOS?
Yeah.
I don't know, probably the next guy.
Good afternoon, sir. Sir, I want to know if I write a code, how can I check the complexity or the efficiency of the code?
Again?
If I write a code, how do I check the efficiency or how do I go about checking the efficiency or the complexity of the code?
Testing the efficiency, you have to time it. If you're on Unix, you just put time in front of a program. You could just end up running program. If it's a bigger system, you have to put in probes or something. With C++ 11, it's really easy to time the code by putting in start time and stop time and measuring it. But you can either do it with an external timer or putting probes in and subtracting and start time and stop time. Or you could use a profiling tool. I'm a little bit addicted to sticking in probes. That's my favorite probes. But for a simple thing like I showed you, the time for the sort, you put in start time, do the sort, stop time, print out the difference.
Thank you, sir.
That's the simplest approach, and it works beautifully. And I'm actually quite disappointed to see how few people do something that simple. You don't need something complicated. There's a lot of hands-on.
Sir,
Yeah.
I'm new to the programming world. I wanted to know what makes the difference between a good programmer and an excellent programmer.
Between a programmer and what?
Between a good programmer and an excellent programmer.
One of the pretty amazing things is that the difference in productivity between a good and an average programmer is enormous. 10 times, 20 times, 100 times. And it's a bit hard to quantify what makes that difference. I think that a lot has to do with understanding of the fundamentals that's going on. That is, if you believe in magic, you will do things without knowing why you are doing them, and you will produce systems that behave in ways you didn't expect, and you spend a lot of your time debugging. There's few things I hate as much as debugging, so I'll do just about anything to make sure the bugs aren't there in the first place. And so a lot of good programmers, they know the data structures, the algorithms, they know the machine architectures, they think in terms of higher level concepts rather than just throwing code together. And the really good ones, it's a bit like artistry. That is, you can see they're doing it, but it's hard to explain. I mean, if I painted something, you wouldn't confuse it with a Rembrandt or any other real artist. And you can study the real artist and see what they're doing, but it's really hard to replicate. It's not. Programming is not an assembly line skill. It's a high level activity, and people want to reduce it to a low level manual skill. I just getting it wrong. They're creating the average programmers are very slowly producing huge systems that are hard to maintain. And so I strongly encourage at a higher level to do things and expressing things in data structures, the algorithms is one great help. The other thing is just thinking things through. Good programmers basically try and understand their application domain. If you're going to write some code for, say, some historians, you have to read up a little bit about the kind of history they are dealing with so that you can speak their language and you can understand the problem correctly. A programmer that's just a programmer is close to useless. You have to have somebody who can understand the problem area. So that's one reason I'm a fan of master's degrees and double majors, for instance, so that you have an area that you understand that's not programming.
Thank you, sir.
Good afternoon, sir. Now if we look into Java, it has got compulsory exception handling. So my question is, what is the reason that you did not put that instead of, in the upcoming version of C++ instead of segmentation fault?
So Java initially sort of borrowed the C++ exception handling, and then they elaborated on it. And so they have dynamic record exceptions and check exceptions, and it's a bit of a mess. And we try to enforce exception handling through writing a lot of try-catch blocks. I think it's a mess. And so what you get is, if you get a language where you have to write a lot of try-catch, then you feel a desperate need for finding. If you write code where you're trying to avoid try-catch, and instead follow the RAII paradigm, where you let classes define constructors and destructors do the cleanup rather than explicit cleanup, you get very little try and catch, and therefore you don't feel the need for finding. And basically, I decided that adding finally would encourage people to write their own kind of code at a too low abstraction level.
Thank you, sir.
Good afternoon, sir. Sir, what were the struggles or difficulties you faced during the initial stages of creating and developing C++? And what are the things that you learned throughout as the journey progressed that you would like to share with today's programmers?
I'm sorry, I didn't understand. We're both speaking English, but different dialects and different pronunciations, and I haven't been in India for long enough to get used to it. So apologies for my part, but we could please try again.
Yes, sure, sir. So what were the difficulties you faced during the initial stages of creating and developing C++?
Okay, thank you. Let's see. I had a pretty good idea of what I wanted, and I had the basic skills to write preprocessors and compilers. So that was not the problem. I think I had a fair amount of thought about how to limit my work to something that could be useful reasonably soon. I did not want to do a grand design for the future. So I thought hard about the order of introduction of new features what I could do now, what I could do efficiently. I thought hard about what kind of principles would allow me to do useful things and avoid things that was just there to be pretty. And then I thought quite hard on how I could get people to use the language. That is, what kind of facilities would help them, how would it be easy to port to new machines, and how would it run efficiently enough. I very soon came up with the zero overhead principle, which is that if you can handwrite it faster than using the abstraction mechanism, then there's something wrong. And so, for instance, we have an overhead compared to C, systematic overhead of 3%. This I considered a disaster, and it was removed in 2 weeks. Performance is very, very important in the C, C++ world, and even more in those days, and so I concentrated on that. For teaching, staying very close to C for things where I didn't feel the need to make changes was important. I didn't want to teach people how to write a loop or to call a function. I wanted to rest on some existing language, some existing user community, and I chose C. C was a far less popular language then, far less widespread, so it's not an obvious choice, but it was pretty obvious when you switch it down the corridor. And he can explain things to you. The other thing was I realized by generating C as my assembly code, I could run very easily on a lot of systems and basically hijack a lot of the technology for generating good code. And that turned out to be a really good idea, because I think C is a very good low-level language. It's a very good assembly. But if you stay at that level, your productivity goes down, your maintenance cost goes up, and basically you think and work into low level. So I wanted to get beyond C, but I wanted to rely on it where it is really good.
Good afternoon, sir. Sir, I would like to ask you a question regarding the direction of C++ going forward. So we are seeing that some features like lambdas, automatic type inference, that are kind of popular in some other languages, say Python or JavaScript, they are being gradually included into C++. So going forward, what kind of constructs or paradigms do you see getting into C++, or what is the criteria you use to judge to really include new features into C++?
That's a very hard question. It doesn't have a really good answer. And the reason is that the C++ committee is sort of 100 people in a room and maybe 300 people in the larger community. And it's really hard to have a simple answer to do with direction for a group like that. I can answer the historical part of that question reasonably well. I have been looking for more elegant ways of writing algorithms just about forever. And so, for instance, also, which you say correctly, many other languages first came into C with classes in the winter of '83. And I was forced to take it out again, and we got it back. Many people see, oh, they're imitating language X. X is their favorite language. No, it's just we couldn't do it before now. Lambdas came in as a terse notation for function objects. And we've had function objects and used them over many years, and now came the time where we realized that a better notation was important, and we produced one. And the better notation was provided without loss of efficiency as usual. And so I'm very conservative and slow when it comes to adding new features to the language. It may not look like that when you look at the language, but if you look at how many years it takes to get something, it is slow. And that's the real one. The functional programming community, for instance, has owned a huge part of academia and a huge part of the education system for 30 years. And basically nothing, had nothing to show for it until about 5-6 years ago. And so I was very careful trying to learn from that community and also trying to avoid mistakes that have made people not want to write code like that. And so we're slowly adopting things. Similarly, the object-oriented community was very, very strong, very, very vocal in the late 80s and the 90s. And I very carefully actually avoided going overboard in that area. And I think that has been good because it has led to very complicated systems and very slow systems and very big problems with adaptive things. So I'm trying not to dodge your question, but I have a set of principles that I try to do, like the zero overhead principle and the fact that it actually has to be useful in real applications, not just be pretty. And then I have to go into long, complicated discussions with people in the standards committee about what's possible and what isn't. And I also try hard to work on language features that integrate with the rest of the language and help people that are doing existing things as well as new things, rather than building yet another addition that doesn't relate to something else. This is particularly hard because people with a development mindset will take the first solution that solves their problem and bolt it on, whether it fits or not. So I'm very concerned about the integration of things.
Good afternoon, sir. Sir, one of your slides shows that C is 2.5 times lower than C++ itself.
For one particular example, with one particular library and with one particular compiler, it also said your mileage will vary. That is, when you do this example again next year, maybe the result is better, maybe it's worse. I have never seen C beat C++ in this example. I have seen C++ beat C with up to 10 times things. But you have to remember that this is not a general statement.
I was like wondering because most of the embedded applications we still develop in C and not in C++ further on.
Sorry?
Most of our embedded applications we still develop in C.
Yeah.
So if that is the case, I was just thinking, I just thought that as a generic statement.
I think it's generally a mistake, and it comes from people's belief in that what is a smaller language must be faster, what is lower level must be faster. And then a lot of old engineers who basically never was taught how to program and writes the way that things they've always done. I mean, I have met people that felt like it was too slow to pass arguments as arguments and they have to be put into lower variables and access. They were convinced this was faster and more elegant. No, wrong. I've also met people who felt that you shouldn't have many function calls, so their functions with thousands of lines wrong. They're wrong. And so people can do better, they should do better, and I believe very strongly that people can do better, and that we will eventually do better. I'm an optimist there.
Just one second question.
I never saw a program that could be written better in C than C++ for any other reason than a lack of a compiler. And I made this statement again and again for 20 years and nobody was caught with a concrete example.
That's good, sir. Probably I'll try again to develop a code probably if I can see the difference. I have never tried myself. I've always tried with C and I found it's good working out well. Now coming back to my second question, C++ 11 and C++ 14, that is what you are working on, probably your team.
No, they shipped. I'm working on 17.
That's fine. My question is that the libraries that you are developing, are you actually targeting or has been targeted for security evaluation, or it is evaluated, or it has been graded, or that matter if at all that is being used for the implementation of some of the secure algorithms implementation, maybe say RSA or so on and so forth?
C++ is used in lots and lots of different areas, more than people would use. Some of them has been evaluated. If you look at those WG24 group into security, they have an evaluation of C++ features. They're not perfect, but at least they're better than C. And it has been evaluated in other contexts, like for flight controls. You need a subset for that, because you can't have new and delete. But as a general statement, you can't make one application area too wide. But people have considered it. The Institute at CMU for Security has looked at it, at C++ like in other languages, and some of the embedded standards have looked at it from a different kind of point of view.
So do you suggest this language can be used for the implementation of the secure applications?
No, I'm telling you that it has been. If you go to my homepage, look for the JSF++ guidelines. Those are the design guidelines for C++ users, design guidelines for the Joint Strike Fighter, that is the American F-35s. They're there for flight. It's a C++ plane. So the F-16s now. So it's been done.
Thanks.